to having me here. And I really, really apologize for the and for being late here and for the confusion with the time zone. I actually just walked in the building. I was supposed to be working today, and they didn't have the room available for me because of I requested for 11 o'clock. So I am presenting this from a very unusual place for me. I'm presenting this from a parking lot and this picnic area where people are eating here, having food. So in any case, let's get this started. My name is Armando Lacerda, and I work with Design Mind down in San Francisco. Design Mind is a BI company. We do BI, big data, data analysis, and a bunch of other things. I myself have been working on the IT field for over 30 years. I'm a developer at heart. I started as a developer. I started working with databases back in the early 90s with IBM mainframe on SQL DS, and then with Oracle. And then by the second half of the 90s, around 97, 98, I was introduced to SQL Server 7.0 when Microsoft was just releasing it, and I got seduced by the dark side of the force, and I moved from Oracle platform to SQL Server, and I've been working with SQL Server since then. So this particular session, I put this session together last year when I was working with a friend from Brazil. I'm from Brazil, by the way. So I was working with another friend that lives there in Brazil on a big data project. And the idea is we want to use Power BI, Design Mind, and nowadays I'm very focused on Power BI solutions. So they want to use Power BI to present big data, actually IoT data flowing through big data. And Power BI has its limitations to get the data showing there. We're gonna see some of these what are these limitations as we move along in here. But the idea was we want to show insights about big IoT data, sorry, flowing through big data structures and getting to Power BI near real time. And there was an interesting challenge. It was not much in my field, but it was a very interesting challenge. So we started working that thing together. We got it to work. It was very successful, and I made up this presentation here to show our experience. So the idea here is how to get insights using Azure resources and presenting data in Power BI. And the little formula created here back then, I actually should change some of the elements of this formula now. But the idea here is we can get this insights using massive data ingestion coming from IoT data streams, pretty much using Azure Functions and IoT Hub and SQL Server. Actually, Azure SQL Database, which is not the VM, plus Power BI. That was the solution we put together. So sorry, I just hit my microphone here. So before I go into the implementation of these things, let's first take a look what is the Lambda structure. That's the agenda for the next hour, at the top of the hour. So the idea is how can we get live data in Power BI? Actually, I moved this to the end. They're going to focus more on the bottom line here. So you're going to understand the live data in Power BI limits close to the end of the session. We're going to get started first with the Lambda architecture and how to implement using SQL Server. That was one of the challenges because SQL Server it is deemed by most people like it cannot scale to the volume of data we need to deal with in big data. And in many aspects, that's really true. But we came up with a solution that can do one branch of the Lambda architecture and using SQL Server. So we're going to take a look at that. And also going to see how Cosmos DB can also be an option in here. On this slide, I got this book. Here's one of the most talked about books on the idea of big data from Nathan Mars. And it's a great book. It really explains the idea of Lambda architecture, which I'm about to dive into in the next slide. But if you want a reference about a book on Lambda architecture and how to deal with massive data ingestion, this is the book to get started with. There are many other books, but this is the one to get started with. So I read this book, I started with it, and the thing is, this book is focused. The solution, they actually go through a solution implementation through source code, but the solution is completely focused on open source implementation, using Java libraries, using Linux hosts to get the data going there, and I think a Hadoop backend. So, and that's not my platform. That's not the ecosystem I live on. The ecosystem I live on is in Azure. So it was a very educative book, to give me the guidance about what I was to implement, what I need to implement. But the real idea was how I can implement that same path, that same resources they put in there in Azure. So this session is all about that. Let's implement that idea, but in Azure. And by the way, just a disclaimer here, I'm going to show you one of the options, the option I did last year. Since last year and today, a lot of new Azure resources came along, and they should be considered. I'm going to mention them as we move along. They should also be considered. So please don't take this presentation here like this is the way or the only way to implement Lambda architecture in Azure. There are many other possibilities because Azure is a collection of over 100 services, and a few of these services, they almost overlap each other completely. So there are more options than the ones I'm going to show to you here. Then please feel free to interrupt me if people ask questions as I move along, because we're kind of a short in time. I just go through these things here and do the demos that show some of the pieces I have in Azure for us. But if anyone asks questions there on the panel, please just when I catch my breath here, you can go ahead and jump in and let me know about the questions if I can answer. Is that a deal?
Sounds great. Thanks. Appreciate it.
Perfect. So what is the Lambda architecture? The Lambda architecture, like I said, I'm a developer, and I'm a C# developer. And a few years ago, Microsoft came up in implementing the C# a way to do what we call anonymous functions, right? And anonymous coding, and they call that like the Lambda coding style into C#, the programming code. And also in mathematics, arithmetic, and statistics, we have the Lambda also using there. Actually, the word Lambda is used in many areas of society, including categories of people in some psychology books. So the first time I read Lambda architecture for big data, I say, oh, what's Lambda now? What they use the name Lambda for? So it became like a wild card for whatever. But the idea of the Lambda architecture is based on the Greek letter, the Lambda letter, and the Greek letter. Actually, I should have a picture of that in here. Let me just get into a browser just quick so you can kind of grab the idea. Lambda Greek letter, and it goes like this, right? This one here. So the idea of the Lambda architecture is like I have one stream and I split this stream in two. That's the idea. The character to the left is the uppercase lambda. The character to the right is the lowercase lambda in Greek alphabet. So that's the idea of lambda. You get one thing coming in and we split it in two branches. That's the whole idea. That's why they adopt the Lambda name for the Lambda architecture. Meaning, we're going to have one data stream, and in my project, in any massive data ingestion project, this stream comes from any place related to your business. Like if you're a web online retailer, so you get your website, and your website is monitoring how people browse and how interested they are in your product. So every single click generates a stream of data to your big data repository. So your website is your stream source, is your unique stream source, a source of data into your system. If you are like in a manufacturing company, like I'm here today, so we get all this machinery around. They have hundreds of machineries around here, and each one of them they have dozens of sensors monitoring many aspects of a particular device, a particular equipment here. So all these things, they generate streams of data that's going to land at some repository. So that's my data stream, my data source coming to my analysis system. And the problem here is usually this is where the massive stands for. The data coming from there is really massive. It can be really, really a large amount of data. Like when you're talking about cars and auto driving cars, self-driving cars and these things, there's so many sensors, there's so many information coming through that it's really impossible to deal with it at once. So the first thing that we do in the Lambda architecture is to fork that data. We need to have some piece of system that will collect that data and make sure that we don't lose any of that information, and we'll move that and we'll deliver that data to the actual processing spot, the actual processing code. And that's usually done by service bus services, someone that's gonna just catch the data and store it to safekeeping in a stage way. It's not to keep it forever. It's just to avoid losing anything, and put in a queue to be delivered. And then on that queue to be delivered is where it's going to be split in two. And here's the big thing: we don't have computing power today to process all the data we are reading from these sources online on the fly. We cannot process its entirety, the complete amount of data at once. So the Lambda architecture will split it in two. The Lambda architecture will split it in two. One, it's called generically as the data sync branch, and the other one will be the data queue branch. And the idea here is all the data I'm receiving will be processed later as a collection, as a full collection of data, like a batch. So the white branch here that I'm calling the data sync, you're going to also be named the batch processing. So data is just flowing through my pipes and being stored, placed on some people call it the data lake, some people call it the repository. It's just being stored as it comes on a place where it's going to wait for a batch process to run at a particular time we come to schedule. So that is deferred processing, the batch processing. On the other hand, we're going to have the same influx of data being delivered at the same time to another branch, which is called, here I'm calling the data queue to be processed. In many literatures, you're going to see this one here as the speed lane, right, or the speed track, which means the data is going to come in here and is going to be landed on a repository to be processed on the fly as it comes, but not on its entirety. I will have some kind of discretionary process, so it's a discrete processing going on here. They will look into the data that's coming in, and they will apply some criteria that generically they would go like, is this data important to show on the fly online right away? And I define those criteria, right? Define those criteria in my code. So if the answer is yes, I'm going to move this data into the speed lane to reach my visualization point. In this case, it's going to be Power BI and the Microsoft ecosystem. Otherwise, I would just discard that data. That data is not that important. The things are working normal, let's say. So really don't have to worry about that. And so just discard the data. So the speed lane here will just emphasize or will collect data that needs to be shown on the fly that will require some sort of immediate action or is considered that important to the business that must be informed right away. On the other hand, on the upper layer here, on the data sync or the batch processing, like I said, the data will be accumulated on a repository, and at some point in time that you come to schedule according to your criteria, a batch processing, some code you created will come in here and will process this data all together. Like you could, for instance, skew the data to create some dimensions based on the data that's coming in, and learn some new dimensions. You could oh my God, the word is failing me now. You could aggregate the data or reduce the granularity. That was the statement I was looking for. Reduce the granularity of the data. So let's say you're working with cars, self-driving or cars with sensors, and you work with each individual car. So if something happens on a particular car, you wanna show on the speed lane on the discrete processing right away, like the car is getting a flat tire or something. But on the batch processing, you really don't care about each individual car. You just want to see how many miles were covered by a collection of 5 cars that work in a group is supposed to be working in a particular area. So on the batch processing, you do all this granularity reduction or data skewing when you're doing there, and conform the data that's coming in a very unformatted way. The one thinks about IoT, and specifically on when you choose like JSON formats, like it's schemaless. So when you go into batch processing, you may want to probe the data you are collecting in and put into some schema that will be leveraged by the next step of the layer. And the next step of the layer is actually collecting the data that was processed, either by the batch processing or the discrete processing, the speed track here, and make it available to the visualization layer, which is the next one, right? To the visualization layer or the query layer. And then you could ask, hey, Armando, since I already have the data over here in the data sink, in the data queue, and the data is being processed in here, why can't I deliver the data straight from my discrete process into the query layer or the presentation layer? Why could it, instead of, why do I need to have this data repository in between these two? That's pretty much for, depending on the layer, like on the discrete layer, this one here is just for throttling. And the idea of throttling here is I may have like 3,000 sensors sending data on the same second to my discrete processing. So I chose a particular platform, particular technology to process that can scale to that 3,000 events on the same second. But there is a very good chance that your visualization layer cannot process 3,000 calls a second to update the interface. So the interface will be updated like once a second or once every 2 seconds. And then we need to throttle what this guy is producing to what shows up in the query. And that's what this database here in the middle is for. It's to keep the data up to date according to the discrete information that's been processed and move forward to be shown on the interface. But at the same time, caching it so the query can have time to render, perhaps be able to manipulate it by the end user. And when new data comes in, the query will come on a short schedule, but not as fast as the data comes in, to be refreshed for the end user. And on the other hand, this data servicing here for the query is when my raw data from the data sink, which is schemaless, would be schema full or schema compliant, so my queries can rely on a particular structure that was not guaranteed when the data came from the sensors into the batch processing lane. So that's the idea of the Lambda architecture. In summary, is we have a track to process data in its entirety in batch processing in volume and scale. And we have another lane of processing, we call the speed track or the discretionary track, that will look at the data as it goes through and just pick the data that's important to be shown right away. The business is focused on learning about that data on the fly right away, near real time, and make that data available for the presentation layer at the end. That's the whole concept of Lambda architecture. Is that okay? So far, so good? Do we have any questions about this?
No, we're doing great. Keep going.
Keep going. All right. So how to implement that in the Microsoft ecosystem? Well, There are people, there are business out there that try to do this on premise, and can be done, of course, because it's, it's just computers or whatever Microsoft has in Azure. Any company could also implement something similar on premise. But the idea here is, since we're talking cloud, since we're talking big data and then business analytics here in this virtual group, the idea is to leverage Azure architecture for that. So the first design, and of course this is just illustration, right? But the first idea, the first design of implementing this is using Cosmos DB. That was our first approach, because like I said, SQL Server is deemed like not fast enough, not performatic enough. You cannot scale enough to take care of the speed track. On the other hand, Cosmos DB is very fast, very reliable. Cosmos DB, is such a technology that I love. We're not going to focus on Cosmos DB here, but it can do great with Cosmos DB. In a way, we could use, technically, there would be another option cheaper than Cosmos DB that would do something similar, which is the blob storage and perhaps using queues for the IoT service here on the event hub. But the thing with that one is it doesn't scale. Although it's in the cloud, the blob storage has some hard-coded limitations in there. They cannot. There is a limit of 60 megabytes per second in there, and most IoT solutions, they require way more than that throughput. So technically it would fit, but in terms of performance, it doesn't get there. It doesn't scale. So Cosmos DB was our first one for the speed layer, for the discretionary processing, and on the batch layer, we used the blob storage, because that is just storing there. It's gonna be processed later, no big deal. And to get it on the data service layer, we decided to use Azure SQL Data Warehouse to process the data coming from the sources and stored into the lake, and using Polybase support in Azure Data Warehouse in Azure in the cloud to get the data into Azure and do both the skewing and the granularity reduction. And with this data available in both places here, and that's my throttling here for Power BI, we get the data flowing into Power BI right from there. So this is a possible implementation, and we ran that. We did some tests on this one here. The batch layer worked as expected, so that was cool. But the speed track layer, the one down here with Cosmos DB, we had a sensitive problem there. It was not a technical problem, but it was a very sensitive problem, which was budget. Because Cosmos DB, it charges the service charges you based on utilization. So it's what they call the RUs, the resource units you use as you query data, as you input data, and depending how you query data and how the data is organized into the database, you can have a kind of a higher bill. If I have 10 cars today, I have that bill because I have that amount of data going through the speed lane. But if I get 20 cars next month, then my data utilization will double. But the data coming through the pipe will double, and there is a chance that Cosmos DB will be at least 40 to 50% more costly than the previous month. Because I got my data going through, and Cosmos DB charged me based on operations as I go and do operations in Cosmos DB. So it performed well for the client we were attending back there, but it did not, in terms of budgeting, how much you're going to spend monthly on this platform, it was somewhat unpredictable. It all depended on data utilization. So I'm not going to demonstrate this one here, this particular implementation here, but that is a possibility. So we decided to go to another one using Azure SQL DB. And once again, Azure SQL DB has always been deemed as not the best option to do this, because of scalability. And Azure, even if it was running on a virtual machine, SQL Server in its regular way, the way it behaves, traditionally, it really cannot support the amount of volume going through the speed lane. But there is a tip here, and that's perhaps one of the most important takeaways from this presentation. There is a tip in here about, let me see, is it writing? I'm trying to highlight this thing. Here is not highlighting, but you can see my laser point there, right? The red thinking there. The big tip here is about using the in-memory tables or memory optimized tables and memory optimized stored procedures in SQL Server. And let me dive deep into this one here. And I go back to this slide here in a bit so you can understand what I'm talking about. And with that, let me go to my Windows Explorer here and open, I think it is this file here. Let's take a look. I did the same. I presented the same session here on Sacramento SQL Saturday a couple of weeks ago, and I had the source code there. So I believe it's going to show up in here. Let me see if this is the guy. No, I don't need to connect anywhere. I just need to see the code. Yep, this is the code. So what does SQL Server? What does SQL Server? Well, let me rephrase that. Why can't SQL Server support the speed lane? The main issue is SQL Server is a transactional database. And transactional database is the main focus is to keep data integrity. And in order to keep data integrity, they implement lock systems, right? We get the hardware level locks, we get the logical level locks. There's a bunch of locking systems, locking mechanisms inside SQL Server to guarantee that two people will not change the same data at the same time, corrupting the database either on the business level, on the logical level, or in the physical level. That concern does not apply to massive data streaming, because one of the things about massive data streaming is you're never changing something that came before the new data. You are always adding. It's a pending operation all day long. You're never really replacing anything. And as the data comes in through the speed track, through the speed lane, as I accept the massive data coming in, I really should not care about locking, because just get the data in, see what to do with it, and move along. Either discard or move to the next one, next step. The next step could involve an update. But the problem is, again, I don't need the lock mechanism. But SQL Server is designed to do everything on a locking mechanism, unless if you decide to use memory optimized table. This was the breakthrough to get SQL Server to help to support our massive data ingestion, because when you do memory optimized tables in SQL Server, the memory optimized engine does not implement locking. That's the beauty of it. As the data comes in, if you research a little deeper on that one, you see that as the data comes into the table, it gets a timestamp. So when data is queried or processed, even in a transaction, SQL Server looks at the timestamp of the row to see if that particular row applies to the timestamp of the query. So if the row was like deleted after or before a query is running, for instance, SQL Server just skips that row because that row doesn't apply in the time frame of the running query. So bottom line here is, to implement the speed lane in SQL Server, I must leverage memory optimized tables. Keep in mind, though, that memory optimized tables, they have a lot of restrictions when compared to regular tables or traditional tables. For the processing we are doing here, it really doesn't matter. These restrictions really don't affect us. but depending on your business, you want to be aware of some of those restrictions, so you see if it fits your business needs. But this is the thing, right? It's about using memory optimized tables. So in this case here, for the demonstration, I'm running out of time, so I'm not going to have much time to go into Azure and show you the moving pieces. But for this demonstration here, I'm using that taxi New York City yellow cab taxi database that's made available online. And I apologize for to the guy who brought this thing online. There is a GitHub repository where you can download this from. The city of New York makes the data available there on their website, but this guy had some code on, I think, on some Postgres for open source. And once again, I got that thing to work on this demonstration here in SQL Server. So you can just Google that and you can see. So the idea here is I read from those files in Azure Batch to create massive volume of data. So I'm monitoring all the taxes in New York since 2007 to 2017, I think. And I move the data through the pipeline. So when the data gets in here, this table here is keeping the count, the passenger count for every cab. That's every ride actually that is signed by a cab when they start riding. So this table here in the speed lane is memory optimized, so we can keep up with the flowing in here, and there will be coding, adding rows in here as they go through, and I will update my data service on the next call of the Azure function. So this is it, right? Takeaway number one: if you want to use Azure SQL Database on a speed track for your Lambda architecture, you got to use this because this does not implement locking. The second thing is more likely you don't want to keep the data in the database, only memory. Data is kept in memory. So schema only is very important for that one. And depending on the size and volume of data, you may want to have more or less buckets. So I'm going to leave that to you to do a little research on these parameters. So that's one thing, right? This is one piece in SQL Server. The other piece is, of course, we don't want to allow any code to call DML statements to my table, right? We are good developers here. We're good system architects. We want to create that protection layer around my data object, which in this case, it translates to store procedures. So the next thing to do is create a store procedure that will be working on a table, right? So this one here is just inserting the data. So the store procedure is getting the data to insert into the memory optimized table. But here's another trick, right? Very important. These are things most people are not used to. At the same time we have memory optimized tables, we also have memory optimized store procedures. These are called native store procedures, native compilation. If you create a regular store procedure without the native compilation option in there, that store procedure will be like any other regular store procedure. Is going to go to the procedure cache, and query plans will be created every time you call that store procedure, and that is going to slow down the whole process. The idea here is when you create a native store procedure, memory optimized store procedure, SQL Server creates the actual C++, not even C#, it's C++ code, and places into memory. So when this thing runs, it doesn't create a query plan, right? Because the table itself is not as a traditional table. So it really doesn't require a query plan. It's just memory scans. So the code is very, very optimized, really fast. And depending on your subscription level, it can keep up with the massive data coming from the IoT hub or the Azure function taking care of the IoT hub. So that's the thing, right? These are the two important elements, resources to leverage in SQL Server: creating memory optimized tables and memory optimized store procedures, native compiled store procedures. So we don't stumble into query issues in the store procedure and locking mechanisms when we're working with the table. The other thing about this is when you go into Azure and you go to create, let me see, I've got a web browser here somewhere, here. So when you go into Azure portal.azure.com. Let's get there just quick. Design in Mind has given me a MSN subscription to do these presentations gracefully. Those guys are great. And if I go here to SQL Server, let's say I want to create a new SQL Server, see I'm running out of credits, $150 credit monthly. So if I go here into add a new resource, and if I choose here Azure SQL Database, Azure SQL Database has some options nowadays and more options than a year ago. So you may want to investigate those options too. Just put some naming here. What I want to get to is this one, right? The price tier. Keep in mind that in Azure, SQL Server on premises, we have the instance and the database for the instance. So the instance defines performance because the instance is related to the virtual machine or the bare bone hardware you are using to host your SQL Server. But in Azure, the instance, the server here, does not define performance. It just defines administrative levels, administrative permissions for the collection of databases, and also in which data center your database is going to run at. The actual performance is defined by the price tier for each database you come to create. So that's a very interesting thing in Azure. That's counterintuitive when compared to on-premise, because on-premise is really backwards. Now, when you get in here, in order to leverage the memory optimized and native compiled store procedures, the memory optimized tables and native compiled store procedures, you got to make sure you understand you cannot create those artifacts in the standard level. You have to go to premium level. So of course this is more expensive than the standard, but that's the point about the Cosmos DB. If I decide to come in here and say, you know what, I need this DTUs, this processing power, 500 DTUs, with the database size is not really that important. It's the database memory inside that really affects how much data can cache in memory for the memory optimized ones. So yeah, so I come in here and I say, hey, my bill for the database is going to be $1,900 roughly per month. So I can count on that. And that's important for business. Actually, that's one of the most important roles for cloud-focused DBAs, be able to predict costs. If you're not able to predict costs, you're usually going to get someone on you at your workplace, because the company needs to keep costs under control. And that was the most one of the most desired benefits for the client. I want to see the same view every month, regardless of utilization. Now they know that if they increase their data demand too much, we're gonna come in here and upgrade the DTUs for the layer, right? So you can keep more data into memory and process faster. But still, they know what the bill is gonna be like at the end of the month. So keep that in mind. To leverage those resources, you have to do premium, and you have to do the right amount of DTUs on premium. There is this other option here for the vCore that can also be used, and here it tells you how much memory you can have, so we have more control over here to create those elements. And it's not based on DTU, it's based on processing power, which is important for this case, and how much memory you have for this case. For your server. So let's say I don't have that much data, I can live with 400 gigabytes, but this is the amount of memory I have to use on this particular database. Remember, it's not for the instance, it's for the database, not for the server, for the database. And this is how much it's going to cost per month. So this is a bargain, right? This is really, really, really cheap for the processing I'm doing here if I had to do this on premises. So yeah, so that's about it. That's the most important takeaway. Everything else on the slide deck here about the Lambda architecture, they refer to other elements, like I use Azure Functions on the final element in here to process the data coming in and decide if you should go into the database or not, if it meets whatever criteria I want to keep, that you put in the memory table. So the next Azure function that runs every second can get the data into Power BI. The batch lane is not really the focus of this one here. We're not going to talk about Azure Data Warehouse, but one of the things we added here was machine learning. We got some machine learning going on, learning about trends and like try to predict travel time in between places. So there was an interesting POC with that I did with that one in there, and the code in Azure, the whole implementation. What is my Azure thing here? The whole implementation goes like this. I have here SQL Saturday LA. I have here application insights to monitor things going on. I got an event grid to process the batch lane every time I got 500 gigabytes of data through the pipeline. I get here Azure, a bunch of Azure functions and the files where I read from. So my Azure functions in here, they are made in C# because I can attach them to the IoT hub that was there on the list. I can attach them to the IoT hubs. And the Azure functions, they perform really well by nature. Azure functions are really, really scalable. They are the way to process this massive amount of data coming from the sensors. And for instance, a sensor came from a message came from the taxi, from a sensor in the taxi. So a ride just got started. So my code in here, this code is being called by the IoT hub. It signed up for the IoT hub, and it just goes like this. My internet seems to be kind of slow now. So yeah, that's the piece of code I have. Just a hookup to the service bus in SQL Server. In Azure, and then check if this is a hacking code here. If it's the end of the write, just wait about 2 seconds. So the write doesn't start and end at the right time. So I have taxes in parallel running, getting people around, and send it through the event hub again to be processed by the discretionary text field. So this one here, this code, get the data and calls the store procedure with the information that came from the IoT hub and processed by the ticker. So the code is pretty simple. See, pretty straightforward. Open connection to SQL Server, call the store procedure, send in the data, and off we go. And that's the major thing that this example differs from the book, from the Lambda Architecture book I have shown you. On the Lambda Architecture, they advocate that we should use the same language, same programming language, and same database technology all across the Lambda Architecture. And that's a good tip. But in my case here, because Azure is so plural, we could use C#, we could use Java, we could use PowerShell, we could use so many other languages in there. So that's one of the things that Azure doesn't really conform with the original Lambda architecture. And the last thing is when using Power BI has a restriction of how many, I'm sorry, Anna, I'll be right there. How many times it can upgrade from update the data set. So you cannot use direct query for this sort of a scenarios, the real time online. So what you're gonna do is using the stream data set in Power BI. So there is this thing in Power BI called the stream data set, and can only be done in Power BI service. So if I go here into Power BI service, powerbi.com. Yeah, Suresh is there. He can get started. I'll be there in 2 minutes. Sorry, guys. I'm expecting another meeting here. So I'll be wrapping up this, and I'm going with Anna in 2 minutes. So if I go here into Power BI, what a crazy day. Well, I mixed up the time zone is really bad. So if you go here into Power BI and you go into a workspace, if you go here into the dashboard of the workspace and you want to go and create an element on the dashboard, you can go ahead and create a stream data set. And the idea of the stream data set is Power BI doesn't go for data. Power BI expects code sending data to it. So you can create a Power BI, for instance, a Power BI API streaming data set, and you define this like defining a table in here, define the columns you're expecting, like ride ID, for instance. I have this ride information coming in there, and then I have, you know, passengers, how many passengers I have in there. So this is a number. This is an ID. Perhaps I don't need because it's summarized, but in any case, tax ID in there. So it expects to receive a JSON code like this. And once you've defined, let's see, the data set here is business analytic virtual group, for instance. So I come to create. And what it does is it creates an endpoint, see, a push URL for code to send data in. So I got the API created, and in my model in here, if I go back a couple slides, in my model here, I will have, okay, it doesn't want to scroll back. So let's see here, 12. Yeah, there we go. So this is the slide here in the schema here. I have this Azure function pulling data from the SQL Server and send to Power BI once a second, because Power BI has its physical limitations, you know, hard-coded limitations on how many calls you can do within a second and the max amount of data you can do in a second. Well, that was really quick, and you know, I really had to speed up, pump up my velocity here. I apologize for the rush, but that's the message.
Apologize for the mess up. I'm sorry, the time zones and everything.
Say that again?
No, I'm just sorry that the mess up with the whole time zones and everything, but I'm glad you're able to find a location and able to present the information still. I was able to track down your contents from the from your SQL Saturday event, and I posted those in the handouts for your slide materials. So that was great too. I want to thank everyone for being able to join us and hanging on for the content, the presentation. Armando, I know you have to head out. We do have some questions that were posted, and I'll just probably send those to you in a follow-up email, and then we'll try to get those posted out to our attendees. So
yeah, and if any attendee has any questions, you can reach out to me too. You can just email me at armandolacerda.com instead of the Design Mind email. Design Mind is more for business at Design Mind. So if you want to reach out to me, you can also do you can also do Notepad. You can do me at armandolacerda.com.
Oh, great. Okay. All right. Well, thank you so much, Armando. I appreciate you taking the time and presenting to our community. Great content. Really neat to see how all that works with the Lambda architecture and everything. Thanks for the presentation. Thanks everyone for joining us. And we'll make sure that we get this recording up there posted, and we'll get the content posted to our event site as well.
Thank you for the opportunity, and I really apologize again for the mess up with the time zone, but I'm glad we got something delivered today. So thank you so much.
Yep, thank you. Thanks, everyone.